Yeah, the mic.
Hello, everyone. I love being the first speaker because I am the one who will get to know any one of you or every one of you. So by show off of hands, who in here are engineers, developers, students? It's a very fun way to recognize a recruiter. No, you are welcome to if you're a recruiter. So today we're going to talk about context and React Redux. And of a show of hands, who is for context? If you have to choose one. React Redux? Okay, so it's almost like 2080, I would say. Okay. Well, who am I? My name is Julia. This is a QR code to my LinkedIn. If you ask me about my age, let's just say I am this young. I remember this one time I asked my mother for help with my computer, and she said, "You have to come here if you want me to help you." And I said, "That's physically impossible because I can't bring my computer." This was far back, and now we actually have laptops, so that's good. I have a master's degree of science. I am a full stack JavaScript developer, also TypeScript developer and instructor. And I'm working at SALT, which is the School of Applied Technology. And at SALT, we are educating developers. We have educated approximately 500 developers. So if you are looking for a developer, I am the one to talk to. But let me give you a little background story to this talk. I reached out to my community and it said that I'm going to do a React special presentation. So what should I talk about? And to summarize a very intelligent discussion to a very stupid sentence is that managing state is hard. Redux made it simple. This doesn't necessarily mean that it's easy, but it somewhat made it simple. But if we talk about managing state and how hard it is to manage state, managing state asynchronously is even harder. And Redux uses thunks to handle this. So what the thunk is a thunk? A thunk is a piece of code that does some delayed work. Let's look at this very simple pseudo example. We have a log function here. We have a thunk. And when you call the thunk, you pass it the actual dispatcher. And then it performs some kind of logic or a request to a server or whatnot. And once it's done, it's going to dispatch this log function. But why am I saying all this? Because in the release of React 16.3 in 2018, the new context API was released. And I'm saying new in quotation marks because it's not actually new. It was just updated so it was more accessible. It was funny because like the internet became like this whole meme. Like it was almost like, you know, rapper artists dissing each other, but now it was just useContext and React Redux. So the articles were screaming that this is the death of Redux. And Redux replied, "The reports of my death are greatly exaggerated." So when we're talking about managing state and what technologies we should use for this, I usually look at it through three perspectives. Number one is, okay, how do we manage state asynchronously with global state and dispatches? I'm not talking about a counter example here, okay? Number two, optimization. So what design patterns are being used? What's the size of the bundle? How many re-renders? Like what's the life cycle of the components? And obviously setup and boilerplate using their own best practices. So who in here has actually used Redux before? Who in here hates their boilerplate? Who in here knows about Redux toolkit? Oh, that's good. Oh, all right. I like it. Anyway, so to get this up and running, we need to set up and think about some things. Libraries, selectors, dispatches, reducers, thunks, action types, and provider in a very simple case. So let's look at each one of them. As we all know, context is already inside our React framework, React Redux. We're going to look at the actual toolkit. And when you're using Redux, this is the library that you should use. And we're also going to look at React Redux library. All right, to set up your selectors and dispatches in context, you're just using the hook, useContext. And for React Redux, you're using useSelector for your selectors and useDispatch for your dispatchers, which is inside the React Redux library. Who in here still uses class components, by the way? Oh, okay. That might have been a recruiter. I don't believe you. No, I'm kidding. Anyway, so to set up our reducers in context, we are using the hook useReducer. But in React Redux now, because of our fantastic cool toolkit, we have the built-in method createSlice, which we can pass in our extra reducers. And extra reducers are reducers that handles thunk actions. Talking about thunks, the way we need to set up this in context is a little bit manually. We have to use hooks for this, or you can set it up yourself as well, but I've chosen to use the use callback hook for this. React Redux, however, has its own built-in method create async thunk, which also gives us access to the thunk API. We're going to talk about this more in depth. As for our action types, so since we're handling asynchronous or managing state asynchronously, we have to look at promise-based action types, meaning what happens when it's loading, like pending, fulfilled, or rejected. In context, this is a little bit manual. We're going to look into that as well. So that's why I call it customized. React Redux, yeah, it's a little bit customized as well. But however, the promise-based action types are actually embedded in createSlice and createAsync thunk, which is really good. And then we have our providers. Context, just you get it when you create your context. And for React Redux, it's within the library, React Redux itself. So what are we building today? We are not going to build a counter. So we have like this kind of authentication service where I can upload some images. Everything is being done asynchronously. So hello, whatever, whatnot. Don't think about the UI. I'm not a UX designer. All right, cool. So in case that didn't work, yeah, it worked. You should always have a backup, people. All right, let's look at our component structure and the differences between the context and using Redux. As you can see, they are very similar. So everything in color is for context specific or Redux specific. But as you can see, they are all set up in the same manner. I love clean code. So all the way down is the same. Anyhow, so the only thing that difference them is what you import and how you're actually accessing your state and your dispatches. We're going to go back to our table of content. And we're going to look at this application through all the library selectors, dispatches, reducers, and thunks, and action types and providers. So for context, we need to set up our reducer by the hook useReducer. I think everyone have seen this before, right? I don't have to explain what a reducer is. Anyway, here you can see that we have an auth reducer and we have action types for the fulfilled and pending and rejected action. And inside our provider, we can access this with our useReducer and just pass it the actual reducer. It's a little bit clunky, so to speak. However, in React Redux, it's really nice because we have the createSlice method that's built in, and here we have the extra reducers. So in the extra reducer, we have a builder, and for each builder, you can add cases. So sign in pending, sign in fulfilled, signed in rejected. Everything is being handled by the thunk API. As for our thunks, the way we have to set this up in context is also a little bit clunky. I've already explained what a thunk is. But here you can see the actual action of sign in at the top. And here we just want to say whatever happens when the promise is pending, fulfilled, or rejected. A lot of boilerplate, right? Anyway, and then inside our provider, we can access our dispatch, and then we have to, I call it thunkify the dispatch itself, so that we actually can make this asynchronously as well, right? So inside our component, the only thing we need to do is to pass the actual action into our dispatch. Same thing as with React Redux. However, the create async thunk makes this a little bit easier when it comes to Redux. We have our action here, sign in. The only thing that is a little bit manual is this part, but however. Here you can see that the pending and fulfilled and reacted and rejected part of your state is being handled by the slice itself. When it comes to the action types, like I said, in context, they're very customized. And this is just me being lazy. So whatever I pass in here will actually generate all of my actions types for me. But I need fulfilled, I need pending, I need rejected as well, because I am managing my state asynchronously, right? However, in Redux, as you've already seen this code snippet, it's already built into the create slice and create async thunk. As for our providers, for context, you just create your context, sorry. And as we see here, we're just passing the state and dispatch, which is actually the thunk dispatch itself, which we created with our use callback, if you remember. And then we just wrap our app component with the off context provider. React Redux is quite similar. You do the configure store instead of before you did the create store, if you remember, but now with the Redux toolkit, you're using configure store, and you just wrap your app component with provider passing the store as a prop. As for my conclusion, I think it's easy to see what side I'm on. Who in here thinks that I'm on side context? Redux? Yeah. However, are they comparable? Setting up a boilerplate for managing state asynchronously is clunky with useContext. It's a little bit of inventing the wheel, because Redux already provides us with a great library for doing this. And Redux is using the context API under the hoods. So summary, I wouldn't even compare these, and especially not with a counter example. Number two, would I use either of them to manage my state asynchronously? There's a lot happening within this field right now. There are other libraries for this that provides us with more advanced design patterns, such as RxJS or Redux observables. And more to this will rise. Number three, would I use either of them to manage my state asynchronously? I wouldn't set up something like Redux to manage state synchronously. For this, useContext is completely fine. Then again, I would rarely manage my state synchronously. I believe this is why developers indicate that useContext is good for example, a theme, because it's fine or more okay to synchronously toggle this. That was it for me. I have the repo here if anyone wants to look at it, and it's also a good boilerplate if you're ever going to do like an MVP MERN stack application. You can also find it on my LinkedIn. I will refactor this to TypeScript after this speech, because TypeScript is better practice for both of these examples, but in the case of simplicity, I chose JavaScript today. Thank you.
Yeah, so kind of currently, if you probably heard, is Uber using mostly flow types for typing a JavaScript code. And basically, most of our projects are still using flow. It's only first projects were migrated like a few months ago. And yet we still have a lot of code to migrate. And yeah, so it happened that historically, Uber has chosen to use flow. And back then, if you remember these discussions comparing flow with TypeScript, there was a lot more, quite a lot of benefits that people were seeing in Yeah. So basically, there was a lot of benefits that people were seeing to get from Flow. So first big one is that Flow is written in a natively compiled language, so it was supposed to be faster. Then it has been built by Facebook, so assumption was that it would have a better React support. So that's another one. And also Flow had a promise that you don't need to write that many types, and it can infer a lot of things from your code base, basically without you manually specifying all the types. Uh, uh, yeah, and another thing was that initially Flow had a lot of focus on making a sound type system. So basically, if you have an error or you have possible error, Flow will tell you. But in the contrary, TypeScript was more focused on providing something helpful for developers, but kind of ignoring part about being too strict. And yeah, so Uber happened to choose Flow, and here is how it played out. So because Flow is written in OCaml, it's much harder for people to contribute to it because like JavaScript developers usually don't really know OCaml. uh, then with the type inference, so Flow is inferring types across whole like all project. So it can be inferring type of something because of usages somewhere else in a code base. And the thing is that this increases type check slowness exponentially with growth of your code base. And also sometimes it introduces very cryptic errors because you have something inferred from usage in another corner of your project. So you don't really see where this error is coming from. And then another kind of funny one about React support, TypeScript actually happened to have better React support. So for example, in Flow, if you know, it doesn't really check attributes on normal DOM elements. So like you can have any attribute and it doesn't type check it, but TypeScript does. And the last one about soundness, considering the amount of bugs in Flow and Flow ignores that you happen to add, that was kind of a bit of a joke about soundness because it wasn't sound. uh, yeah, and basically over time, TypeScript started to win a lot in terms of comparison, what we should use. Uh, one important thing which we particularly noticed at Uber is that Flow isn't very predictable in terms of a roadmap. So when new TypeScript version is released, you can relatively easy upgrade to that. And also, even before it is released, all the planning and the roadmap for TypeScript is actually public, so you can see what is planned, and you can actually participate in that planning discussions. But in case of Flow, it was like once a year they release a new version, and you have a ton of errors from like hell know what they introduced. Yeah, and also, as was mentioned, there is much more active developer community. And one particularly nice thing about developer community is definitely typed. So most of the external dependencies that you might use, they either already ship with TypeScript types or they are typed indefinitely typed. So that really helps to cover all of your code base, including external dependencies. And in Flow, they have a thing named flow typed, and it's not even close in the comparison. So most of the types there are either generated from definitely typed or like half broken or outdated, and it's really not nice. And then another thing with the TypeScript is that there is VS Code, and they work very closely together with TypeScript. So TypeScript has really good developer tooling support. So in editor, and then eventually all of the tools like ES-Build, they have support for TypeScript out of the box. But Flow is kind of on your own to figure that. And then kind of question like why to start migrating now? So one thing is that TypeScript is increasingly standard for typing in JavaScript. So this is like a nice picture with a graph of interest over TypeScript and Flow. So TypeScript kind of exploded and Flow almost going to be flat. And another one, which is kind of also about these breaking changes possible in Flow, which are usually not in that way in TypeScript, is breaking changes. So recently, if you heard, Flow introduced something named types first approach, which effectively moves Flow to be a bit closer to TypeScript. So type inference works with types first on much smaller boundaries. And in between models, you need to have type definitions, and only that is exported, but not like random inference across whole project. And together with that is that migrating to types first from previous Flow is kind of comparable on effort with migration to TypeScript. And so it's kind of like a natural push that we are not going to types first, instead we go to TypeScript. And also in the open source community, there was also quite a lot of pushback for Flow. So some projects which initially used Flow were migrated to TypeScript. So a first big one was kind of a material UI. So they were trying to type a component library with Flow. They had a lot of issues. They had a lot of issues opened like bug reports for Flow. And basically, they were, as most of the Flow issues, staying open for years and not really moving. And so they were fed up with that, and they removed Flow support and migrated completely to TypeScript. Next big project that migrated was Jest. So basically, when maintainers were no longer from Facebook, it was migrated to TypeScript because who wants Flow? And and another one, which is kind of related to this presentation, is Babel. On this tooling that I built, it was actually using Babel. And as part of building the tooling for converting things from Flow to Babel, I was also converting Babel. So if you've seen Babel already in TypeScript, and that's kind of our contribution there. Yeah, so this is like common issues for migration tooling that you might find for migrating from Flow to TypeScript. The biggest one is that people usually working on it only until the point when they migrated their code base. Basically, until there is like really big companies migrating, it's not at the level that you can just convert and it just works. Yeah, and then as part of that is that only part of features are usually supported, because like if you have some specific feature used in two places in a project, it doesn't really make sense to build a generic solution for that. It's easier to just convert it by hand if your goal is to convert a specific project. And then another one is that almost all of them are focused only on a syntax part, but they are not converting built-in types. And if you know, the Flow is actually shipped with things like React type definitions or DOM library type definitions. And these might have a different type names, different arguments order, and things like that. And that also needs to be converted. And then another one is that for almost all of them, you need to really carefully review what was converted, because there is no guarantees that converted code will still work after it was migrated. And so looking on all of this, I started building my own tool. It was actually based on existing one, which was a Babel plugin transforming abstract syntax tree from Flow to TypeScript. Yeah, so I started it initially as just contributing to that plugin, but over time I happened to refactor most of it, and as most of these tools, it was already not really supported by people who created them. So I had to fork this, and then there was some additional stuff to do, like fixes for built-in flow types, fixes for the formatting. So I used a library named Recast, for which also happened to need to do some edge case fixes there. and work around in some in library itself. And another one, which is kind of most important, is that I introduced like formal verification step, which essentially is like really simple. So it uses Babel preset flow and Babel preset TypeScript, and it strips types from both versions before migration and after migration. And then it just compares that these two are identical. And then it kind of guarantees you that if you used Babel with flow previously, and you switch it to TypeScript preset, it will still strip types in the same way, and everything will still be working. Yeah, so this is open source. So if you have flow type code base, you can just Google flow.js, and it should help migrating. Yeah, so I briefly talked about this. So with flow.js development, initially I started work on it mostly to have a proof of concept that we can indeed migrate Uber code base. Because if you have this approach that we have some bugs introduced by migration and it needs to be carefully reviewed, we cannot really use it because of how much code we have. So we really needed to have that kind of guarantees that it is working after migration. Yeah, and another thing during working on it, something very useful is AST Explorer. I don't know if you worked on any compilery stuff. That's definitely a must-use tool. It helps a lot in terms of figuring out like how things are working in syntax trees that you have. Yeah, so on things that were migrated. So first project that was migrated, that was Babel. It was around 60,000 lines of code. And after discussing it with the Babel maintainers, we decided to do it gradually. So basically there was a separate pull requests for every package in Babel, and except just converting, they were also including some fixes on top of converting and some refactoring. So that was the approach with Babel. And next one was baseweb. So that's Uber component library. It already had some TypeScript support. So basically there was DTS files for all of the exports, but they were kind of incomplete and bit lagging behind of what was in Flow. And so basically, because we are migrating everything to TypeScript, we migrated it as well. In a baseweb, we had around 80,000 lines of code. And the approach we took is we migrated the whole project at once. So basically, it was converted, some type fixes were done on top of it, and we just landed that, and everything works. Yeah, and then back to progress at Uber. So biggest complication, I would say, was not really about the migration tooling for transforming TypeScript code into Flow code, but about internal tooling. So for example, we have a lot of code generation. We have some Uber specific libraries that needed more code mods. Yeah, so that took some time, almost half a year to implement like support for having TypeScript projects at Uber. And currently we are at the stage when early adopters are migrating. Currently around 10% of code base is migrated. Biggest project that was migrated is Uber Eats, and it's one of most active projects actually. And it contains close to 1.5 million lines of code there. Yeah, so currently we're still improving that migration tooling because there is still more stuff to automate, and there is some edge cases which are not updating some configs properly, for example. So yeah, still in progress. Yeah, so on learnings about converting, so first biggest one is that you can migrate almost completely automating it, and you can have this proper verification. Only part remaining is that you will have some type errors, but they wouldn't block you at the runtime, so you can just suppress all of them. And you will need to only update like Babel preset to use TypeScript instead of Flow, and everything kind of works. Another one is that usually if you had good flow type coverage, it results in much less TypeScript errors, and kind of more flow ignores you have, worse the type errors in TypeScript are, because like it kind of propagates through everything, and yeah. Yeah, also interesting thing was that there is quite a lot of bugs in Flow which are not quite obvious, and a lot of errors after migration which were caught by TypeScript, they were supposed to be caught by Flow as well, but they were not really caught. And yeah, and the last part, that there is still a lot of places where errors can be caused by differences in type systems. So Flow infers things differently, so it still infers things from usages. TypeScript doesn't do that. It only infers from another things which you use it to declare current thing. And yeah, so it needs to do some manual fixes always. One place it's Flow utilities. So like if you have map type in Flows, you use helper type to do that. In TypeScript, you have syntax support, and they cannot easily be converted. Yeah, so that's on my side.
Thanks, Bogdan. Thanks, folks.
So my name is Andrew. I do not know how to pronounce Uber, but I do know that our internal tools are called UMonitor. That's me. So I'm a senior software engineer. I work on the front end mostly, based out of New York. And that is my corgi, Olive, who is back in the States. So UMonitor. UMonitor is our main alerting and monitoring product. It's a somewhat general umbrella term for all things alerting, debugging, and observability within Uber. For the purposes of this talk, I'll mainly be referring to it as a UI for developers to observe the health of their app. Here at Uber, we actually have some pretty robust UIs for debugging. There's no SSHing into various boxes, keeping them open different terminals, tailing logs, and so on. So why would I want to use UMonitor? A bunch of different reasons. Examples, I want to see an aggregate of all logs that my service is emitting, maybe the warn levels, the error levels. Maybe I want to split them on an endpoint basis. Maybe I want to set an alert based on some metric. And when said metric exceeds a certain threshold, do some action. So if error rate goes above 1% on book rides endpoint, no one can get their Uber. Page our on-call engineers and Slack them. Additionally, it's kind of our one-stop shop for all things debugging. We can look at the dependencies, its general event logging system, and it surfaces debug traces for all of our requests. Architecture overview. As an overview, any company the size and maturity of Uber is going to have a standardized microservice architecture. We've all worked with them. It allows teams to work independently while still iterating quickly and having an easy way to spin up services and call other services without too much legwork. Out of the box, services emit metrics that teams would want to observe on. So, when I call service the downstream service, either RPC, Thrift, or HTTP, all relevant metrics are sent to our time series database, which is effectively the data store for all of the product you monitor. Things like call rate, error rate, latency, and a whole host of other dimensions are recorded by default. Then, working on UMonitor as a front-end engineer, we can query these and surface them to the user however we see fit. This is the stack. I'm going to give a quick overview. So at the very bottom, the most foundational part, the blue box, M3DB. That's the persistent data store that I mentioned. It's a time series database, works specifically well for metrics, storing, and emitting. Above that, the green box, M3QL is the query language that was actually developed in-house. It's since been open sourced, and it's a query language that we use to query the database. The backend language of choice at Uber is Go. You're going to see that in the yellow. So all of our backend services contain most of the business logic on the server. Above that, we just have a standard GraphQL layer. That's the orchestration layer to call the myriad of different dependencies in the monitoring app. Every piece of alerting seemingly calls a different downstream. It gets complex. We're not going to go into it. But for example, the metrics we call M3DB, but we often need to map the service on the on-call rotation of the service, then from the on-call rotation to the users of that service. and so on and so forth. The data structure of an alert lends itself well to the graph data structure and GraphQL. At the very top, we have the standard create React app, nothing fancy. A fun fact about this is that 4 years into active development of it, we've yet to eject it. So we still have create React app managing all the Webpack and build configs. You know, as product engineers, we just rather spend our time building products instead of dealing with infrastructure. So for this talk, I'm going to be talking mostly about the alerting aspect of our monitoring system. It's pretty basic. Have a service, want to alert. Lots of different pieces, such as on-call rotations and such. But for the purposes, let's just worry about an alert being comprised of a threshold, a metric, and a sustain. When a metric goes above a threshold for a certain period, that initiates an action on the alert, such as paging, slacking, emailing, so on and so forth. A quick overview of the stack. At the very bottom is the DB we use that I talked about, M3DB. It's open source, not too pertinent to this as a front end talk, but just know that all services can emit metrics to M3DB to be queried later. M3DB is optimized for reliability and cost of storage at Uber's scale. Almost all the services at Uber are instrumented and monitored using M3. It's open source, like I mentioned. Just Google M3DB. The first link should do it if you're interested. Now the layer that connects to the database, the query layer, this is the bridge between getting the data out of the data store and into usable code. It's the equivalent of SQL, it's a query language. From the docs, M3QL is a language of choice when querying M3 tag-based metrics. M3QL queries generally start with a fetch function, followed up by a list of key value pairs and are manipulated by additional functions in a Unix-like pipe format. However, the syntax is far from user-friendly. There's a steep learning curve. We see 2 examples, standardized queries. These are pretty standard. We have them all over the app. Does anyone want to guess what these 2 do? Shout them out. There's a hint somewhere in there. Sorry? It's proprietary code, so it's on purpose. No, only joking. The one on the left is throughput from one service to another, and the other one is latency for one specific endpoint. Obviously, these are pretty simple. There's more dimensions that these queries can be split on, such as region, caller, and other things. This is a little bit of a trickier one, just a little. What does this do? Error rate split by endpoint, of course. Something pretty simple that all apps should be tracking, but we have to write all of this. As we can see, this is crazy complex, not very user-friendly. It just goes on from here. This doesn't, you can see the problems with this. It doesn't lend itself well to reuse. It's brittle and error prone. Every author query may have subtle differences. Our 400 includes an error rate, or was it only 500s? No one knows. And at the end of the day, I don't really want to learn all that. You know, learning to code is hard enough. I don't want to learn another language that monitors my code. So enter signal catalog. It's the product that we've come up with. It's a higher order query language that translates common use cases of queries to simplified ones. You can see the signal on the right and the resolved query that it gets reduced to down on the left. The most valuable aspect of signal catalog is that it's a library. Signals are stored in Git, so they do have version control. They're written once and reused everywhere. It's like an NPM of metrics within Uber. This is all great, but you might ask why I spent a ton of time going over our backend language when this is a front end talk. Yep. Mainly because these are the building blocks of the most common front end component for all Uber's monitoring suite, which are graphs. All over UMonitor, there's graphs everywhere. After all, that's what engineers want to look at. Using the backend abstraction, we're able to much more easily build front end abstractions. Finally, some front end code. So we're going to walk through a simple example of building something that engineers on UMonitor might want to build. So often we're asked to chart a specific metric on UI on a graph. Above here, we see a trivial example of an imaginary hook that I made up called useSignalQuery. We'd pipe that into our charting library. We actually use high charts, but the details are really not important. And this is pretty simple. It works. Is it extensible? I don't know. We'll see. So the product manager comes in. They love this. They love the chart. Best thing ever developed. And what's better than one graph? 3 graphs, of course. We want them all next to each other. They all share the exact same time frame so we can see when the service went down. So we implement this, 3 more hook calls, 3 more graphs. It's all right. They all share the same time parameters in the function. That's all right. But now they want the user to select the time. Of course, why would you not want to be able to go back in time? So we have the date time component to the left, but now we need some statefulness to the component. A little bit more complicated. We pass the setter in as a prop to the time selector, and we're on our way. Project manager loves this, but they need even more features. They need to see the annotations for the deploys, the outages, the alerts firing, kind of the little up and down lines. So now we get another hook to get annotations and another prop added to each chart with the response from that hook. But now also we have to be considerate of race conditions. The data for our chart comes back before the graph data loads. It's getting a bit more complex. Great. Oh, we forgot that we're in the process of migrating everything from the raw M3QL queries to signals. So some metrics are in queries, some are in signals. The logic needs to be added to the component, and before we know it, we have code forks all over the place. This feels a bit brittle. This feels bug prone. This feels unwieldy. There might be a better way. Enter the framework. This is very not descriptive. We're aware. I fought my coworkers on the name, but lost. So this is an internal framework within UMonitor that we've written ourselves, which has served us pretty well. It's an abstraction of all the reusable code that adheres to the DRY principles. And like any good framework, like React, it's the framework itself. It does all the heavy lifting under the hood, exposing a much smaller surface area API to make developers more productive. Some of the highlights are the abstraction of data sources. So we can call signals, we can call M3QL, which have totally different backends. We can call our logging backend. We can call dependency graphs. I actually just added another data source just earlier today. All graphs share the same context, both annotations, the little vertical lines, and the time context. And I think most importantly, there's declarative syntax versus imperative, which is really at the root of the React way. It describes what the program does over how it does it. The same way in React, you just return some JSX markup. You don't really worry about what it's doing under the hood. Document, create element, document, append element, so on and so forth. You just write it, it renders it for you. So how does it work? We're going to look at some code to see how I can drastically simplify our presentation code. So this is a simple time component. We move most of the logic to the specific time component itself, but at the top level, it describes the rendered markup and contains 0 control forks and logic branches. This is only a couple lines of code, but everything that I have in the code block here renders the time picker. And it actually adds statefulness to the URL, which is nice if you want to Slack a coworker or bookmark it for an incident later. It makes creating graphs super simple by leveraging React context to share context between graphs. We can throw 3 completely different graphs next to one another. As long as they're wrapped in the same context provider, a change to a single one changes all of them, which is often what you want when you're looking at related graphs. Again, check out the animation. The URL statefulness is bookmarkable. And the key feature is that graphs get all of the data source from the query provider. So the React context provider uses context to feed any child element below it with the data that makes a call to the server. Lastly, we can add additional data sources to the same graph by wrapping it in additional context providers. You can see kind of what I mean in the code snippet. The annotation provider, which provides the vertical lines in this case, calls a completely separate API. But as long as our framework knows how to transform the data into a structure that can be rendered, all is well. So final 2 examples of graphs. I'm not going to make you guess them this time. Left is the availability of all the calls that an arbitrary service makes. Right is the volume of calls that the service makes split by callee and endpoint. They all share the same time context, which is changeable by the user by zooming in. I tried to highlight that in the GIF. And we actually implemented other components below it. I know I've been harping on graphs, which is kind of what everyone likes, but the table display and the JSON viewer, which I kind of have right below it in each of the 2 columns, also use the data source query provider, which they know how to render themselves. And in the presentation code, it's only a single line to display the JSON and the table. So this is a pretty robust UI. The source code I have coming up next, this is not proprietary. And everything that we saw on the previous one is on 74 lines. So I don't want to say that this simplifies anything. You know, I'm hesitant for any magic bullet on the front end. The code was simply moved from the presentation layer to the framework layer, but it's all reusable. So in summary, this paradigm has allowed us to iterate really quickly and efficiently, abstracting the most commonly used elements within our monitoring app for easy reuse. That's all I got.